Today we're talking about something that burns money and is really hard to turn into reality, but nobody wants to give up on it. Manned eVTOLs. Not the tiny quadcopters delivering your takeout downstairs, not the DJI drones that took over the photography world, but real flying taxis that can actually take you up into the sky. Everyone around the world is diving into flying taxis. The US is busy test flying like crazy, China is running full-on demos, and Europe, they're going wild writing standards. Back in 2019, EASA released the world's very first airworthiness framework, tailored specifically for eVTOLs, the SCVTOL. It basically became the homework everyone else started copying. And even now, in 2025, they're still rolling out new means of compliance, like MOC5, tightening and refining the requirements step by step. But here's the reality. As of August 2025, not a single manned eVTOL anywhere in the world has received an FAA airworthiness certificate. So, large-scale commercial flights? Yeah, we're still far from that. Let's take a quick look at what manned eVTOLs really are from a technical point of view. And meanwhile, will Europe once again be late to the party, just like with electric cars and AI? A manned eVTOL is nothing like a small hobby drone. Just like the era after World War II when people were designing airliners, eVTOLs today also come in a bunch of different technical paths. Some, like the volocopter Volocity, go for a pure multi-rotor setup. Others build on traditional airplane concepts, focusing on generating lift efficiently and cruising like a conventional aircraft. And of course, there's the ducted fan route, the one that already crashed and burned. It's kind of like the Concorde, legendary, iconic, but not something that survived in mainstream commercial aviation. For multi-rotor designs, the technical path is relatively simple. They rely on multiple small propellers for thrust, and the control logic is basically a scaled-up version of a drone. So naturally, they inherit the strengths of drones: stable hovering, intuitive control, and solid safety redundancy, thanks to all those props. But the downsides are just as obvious. Their lift-to-drag ratio in cruise is terrifying, and with electric propulsion, it's hard to sustain long-distance flight. That's why current designs are essentially slow and short-range. They only make sense for point-to-point hops inside dense urban clusters. So, to preserve the qualities of a real aircraft, another design philosophy emerged. Focus on improving actual flight performance, especially during cruise. This approach is mainly driven by the US. Just like the military Vi-22 Osprey, these designs take off and land vertically like a multi-rotor, but once they transition into cruise, they try their best to become a small airplane, letting the wings take most of the lift and greatly improving the lift-to-drag ratio. The upside? Much better cruise efficiency, higher speeds, and ranges pushing into 100 to 200 kilometers, which makes them suitable for longer intercity hops. But moving from all-prop thrust during takeoff to mostly wing-borne flight in cruise is no simple trick. You have to manage the transition, thrust distribution, stall margins, flight control logic. The whole system integration gets very complex. And then there's the design that's stylish, high-end, and irresistibly cool, the ducted fan concept. Forget practicality for a moment. This is the dream setup most engineers would love to work on. An enclosed fan that cuts noise and boosts aerodynamic efficiency. But while a ducted fan is elegant at high-speed cruise, during hover, it basically turns into an air blender that makes life harder for itself. And to give the propeller that fancy outer shell, You end up adding something like 20 extra kilos, plus you now have to deal with heat dissipation, flow field interference, safety redundancy, all sorts of headaches. And that's why this approach burns the most money, yet makes the least progress. It's a romantic experiment, but also a bittersweet lesson in commercial reality. For any new energy aircraft, batteries are always the hard limit. Right now, the mainstream aviation-grade batteries only offer around 200 watt-hours per kilogram at the system level. And, after you subtract the structure, redundancy, and all the safety margins, the part that's actually left for people plus range is extremely small. That's why today's battery-powered eVTOLs typically end up with a payload range of only about 100 to 250 kilometers. The problem is especially severe during vertical takeoff and landing. The energy consumption shoots through the roof, and the heat load becomes a real headache. That's why you'll notice so many eVTOL marketing materials constantly highlighting buzzwords like high C-rate batteries, liquid cooling, smart power management, and so on. Put simply, for an eVTOL, half of its entire energy budget gets burned in just those few seconds of takeoff and landing. And because pure electric power is so limited by energy density, some teams are now looking into hybrid systems or even hydrogen fuel cells. But that opens up a whole new set of engineering risks, so we'll save that topic for another episode. For a traditional helicopter, the pilot uses the control stick to directly change the blade pitch and the cyclic inputs, and that's how the aircraft is controlled. Even though the mechanical and hydraulic linkages are long and complex, the pilot still gets a very real, very direct sense of what the machine is doing. But for multi-rotor or lift plus cruise eVTOLs, things are totally different. You've got a dozen motors and a bunch of control surfaces. There's no way a human pilot can fly while calculating something like motor 3 minus 2%, motor 7 plus 5%. Impossible. So, in reality, the pilot only gives attitude or trajectory commands, and underneath that, a full fly-by-wire and distributed control system has to figure out how to execute those commands precisely and efficiently. Take the transition phase as an example. Part of the thrust has to pitch the aircraft up, part of it has to accelerate forward. Some lift is coming from the rotors, while another portion is coming from the wings. So who takes the lead and who plays support at any given moment? All of that is handled by the flight control algorithms running in the background. That's why an eVTOL typically has 3 or even 4 redundant flight control computers. It's not because engineers love stacking high-tech systems. It's because a single sensor failure or one control channel going on strike could cause the entire aircraft to lose attitude and trajectory control in an instant. One selling point of eVTOLs is that they're much quieter than helicopters. But there's a catch. The overall sound pressure level may be lower, yet the frequency profile changes. With multi-rotor designs, you've got a bunch of small, high RPM propellers, which means a lot more high-frequency noise. To the human ear, it can sound like a swarm of electric toothbrushes flying by. And for city residents, that kind of high-frequency buzzing can get annoying pretty fast. That's why cities like Paris and Rome, when running UAM trials, have to conduct extensive noise tests and communicate with local communities. They even need to consider how far the flight corridors should stay from residential areas and what time of day flights are allowed. This is one of those things that makes Europe look slow, but actually really matters. Elsewhere, the attitude is often, fly first. If people don't like it, we'll deal with it later. In Europe, it's more like, Convince the neighbours first, then we'll think about letting you fly over their heads. And in this area, Europe can proudly say it's the one place that's truly far ahead. EASA released the SC eVTOL framework back in 2019 and has been continuously updating the means of compliance ever since. Even in 2025, they're still iterating. This is the world's first fully self-contained regulatory system built specifically for eVTOLs, covering everything from configuration and flight control to redundancy, electric propulsion, and even emergency procedures, all written in remarkable detail. But here's the problem. Having the best rules on paper doesn't mean much if the aircraft aren't actually flying. The future market, the flight data, the real-world experience, those might end up being taken first by the US, China, Japan, or even the Middle East. In the US, most eVTOL projects focus on boosting flight performance, more lift, better cruise efficiency. Part of the reason is geography. American cities are simply far apart, and beyond that, the US wants eVTOLs to operate as a full network, city to city, metropolitan clusters, and airport connections. With ticket prices positioned around a business class level, range and cruise speed aren't just specs. They directly define the profit margin. Take Joby and Archer, for example. Their ranges sit in the 150 to 250 kilometre window, and cruise speeds go above 200 kilometres per hour. They're clearly aiming to take over the short-range business travel market that helicopters currently dominate. Then there's Whisk, which is going all in on fully autonomous eVTOLs, backed by Boeing. And Beta is following a much more practical, almost electric airplane plus cargo model. Not flashy, but very solid from a business standpoint. The American approach is pretty consistent. Start by aiming at the hardest version. Fly faster, fly farther, carry more people, and then throw money at the problem until it works. Volocopter, the OG of multi-rotors. Its classic 18-rotor design is built for short, intra-city air taxi hops. At the end of 2024, the company ran into serious funding trouble and entered insolvency proceedings. After being acquired in 2025, it pushed ahead again with Volocity certification and even launched the 2026 eVTOL Sandbox program for near-commercial trial operations. It almost didn't make it, but thanks to a save file reload, it's back in the game, levelling up once again. Vertical Aerospace, the UK's budget-efficient contender. Their VX4 uses a lift plus cruise layout, high wing, tilting rotors, with cruise speed and range targets meant to match the American players. They're now in Phase 4 transition flight testing and only got their permit to fly in November 2025. The plan is to certify the aircraft with roughly $700 million, far below the $2 to $4 billion that Joby or Archer are spending. Think of them as the DeepSeek of the eVTOL world, aiming for similar results, but at a fraction of the budget. Lilium, the coolest idea and the textbook example of a high-risk tech path. Their concept of ducted electric fans embedded in the wingtips and along the wing is undeniably futuristic, but the cost, complexity, and cash burn are on a completely different level. By 2025, the company had essentially entered liquidation or for sale status, becoming what many now call the eVTOL dream that ran out of money. And then there's Airbus. They've been running a whole series of experimental projects, City Airbus, A-Cubed, and more. From the configurations they're testing, it's pretty clear that Airbus is playing the long game, developing eVTOL concept demonstrators on one side, while pushing electric regional aircraft and hybrid propulsion systems on the other. It feels less like they're rushing to commercialize an eVTOL today, and more like they're building a deep tech reserve, waiting for the rules and the market to become clearer before scaling anything up. China's path is quite characteristic. First, build a world-class supply chain for small drones, and then scale that ecosystem upward into manned eVTOLs. Take EHang, for example. Its designs are essentially large multi-rotors, and the application scenarios are very down-to-earth. Tourism flights in scenic areas, short urban hops, emergency response, simple cargo runs. But airspace management and regulatory hurdles are still major challenges that need time to sort out. But if one day the policies give eVTOLs the same level of support that new energy cars once received, starting with pilot cities, scaling up flights, adding subsidies and demonstration routes, then eVTOLs might very well replay the entire EV revolution storyline all over again. So, in 2028, you probably won't be annoyed by a sky full of eVTOLs just yet, but in certain cities around the world, places like the US, Dubai, Abu Dhabi, or Shenzhen and Guangzhou, you will start seeing one or two fixed routes actually selling tickets and carrying passengers. And the ticket price? Roughly the same range as today's premium shuttle vans or helicopter transfers. Not cheap enough for everyone to ride every day, but not so expensive that only billionaires can take one for a viral video. At that stage, eVTOLs might feel more like the Apple Vision Pro of transportation. Expensive, futuristic, eye-catching, but still a long way from becoming something everyone owns. And what about Europe? By 2028, it's very possible that Europe's rules and standards will continue to be copied as the official answer key by the rest of the world. But the eVTOL that actually shows up over your neighborhood to take you to the airport, that might still end up being an American model or something from somewhere else. So, compared with having flying neighbors everywhere, you might actually feel that letting Europe spend 2 more years writing standards is the safer bet.